afternoon. Welcome to one more lecture of analytics course, Applied Analytics, the practitioner's approach on descriptive, prescriptive and predictive analytics. And as you have gone through different basic aspects of it, and we are trying to focus more towards the applied side of this course. Today we are going to do a quick overview about the probability. So, hence today's presentation is the overview of probability. Now that for practitioners, probability is kind of a tricky concept, and quite a lot of things has talked about this. So, we will try to take it from the practitioner's approach what it is. So, let us start with the definition of random variables, okay, the very basic aspects of the probability. And to do that, the first thing we need to think about is this concept called experiment, okay. And the definition that we are going to cover here today is more about the what is an practitioner's, an applied approach. So, for practitioners, the textbooks gives a lot of other definitions. Practitioners, for practitioners, think about it as a process. Think about what an experiment as a process whose outcomes are not known with certainty. So, people talk about tossing the coin and all those kind of things, but let us talk about the an experiment of making tea. Okay. So, we will boil water, add tea dust, add sugar, add milk, okay, then boil and stop, pour and drink. So, when you do all these kind of things steps, then you finally get a tea. If you think about it, you get a cup within which you have tea. Now, you are drinking tea, hot tea. Now, each time when you make the tea, you actually would get not the exact tea, you will get some different versions of the tea. So, what type of tea you are going to get, there is no guarantee of it. You will get tea, but some different versions of tea. So, similarly, if you follow a process whose outcomes are not known with certainty, you know that you will get an outcome, but which outcome you will get, you are not going to be sure about it. So, the process could be a decision making process. For example, let us talk about reducing the price. Reduce price of car. So, Tata Motors try to reduce the price of the car. So, let us take for the time being, let us take Maruti Suzuki reduces price of Swift. Let us say they reduce the price of their Swift car model. Then what happens? How is it going to impact? Well, there is no guarantee that you can have increased sales, okay. You can have reduced sales, okay. Then competition reducing the price, competition less price, okay, etc. There are quite a lot of options. We are not sure what is going to happen. You cannot say that this is going to happen 100%, this is wrong, cannot say that. So, something will happen with some probability. So, that kind of a situation where you are not sure about the outcome of the experiment or outcome which one will occur with certainty, that is called as a experiment. The next concept we need to talk about is the sample space. So, in sample space, when you enumerate all possible options, all possible outcomes of an experiment, that collection that collection, or in a way the mathematical phrase for is it or the set, okay, that collection or the set are called as the sample points, or sorry, as called as a sample space, or not R, it is called as a sample space. Let us clear this. It is the collection, the set E is called as the sample space. So, if you are, let us think about a example of rolling a die, rolling a fair dice. Okay. So, a die has a face. So, die is like a cube, you all know about that. Okay. It has like 1, 2, 3 like this dots. If you are rolling this, the outcomes you are going to get is, you can get the face value 1, 2, 3, 4, 5 and 6. So, this collection of these outcomes, this is what is called as a sample space. This set is the sample space of rolling a fair die. Okay. Fine. Then there are many other ways we can think about doing this as well. We will take an example. If you roll 2 fair dice, roll 2 fair dice, then what will be the sample space? The sample space will be, you can think about it this way, the first die will have a face of 1, second will also have a face of 1, then the first die can have a face of 1, second can have a face of 2, first die can have a face of 1, second die can have a face of 3, like this all the way to first die can have a face of 1, second die can have a face of 6. Similarly, the first die can have a face of 2, second die can have a face of 1, first die can have a face of 2, second can also have a face of 2, then 2, 3 like this all the way to 2, 6. Okay. Similarly, you can think about last option will be, the first die can have a face of 6, second die can have a face of 1, first die can have a face of 6, second die can have a face of 2, first die can have a face of 6, second die can have a face of 3, all the way up to both dice giving 6, 6. Okay. So, this collection, okay, so there are 6 options like here and there are 6 options this way. So, you have 36 different possible options. Okay. So, this sample space of rolling the 2 dice has 36 points. Okay. So, which brings the next concept, sample points. What are sample points? The individual outcomes, in the collection or the set as we called, or the set are called as the sample points. As an example, in the rolling of the 2 fair dice, the face of 4 and 3, this is a sample point. Sample point where die 1 has the face of 4 and die 2 has the face value of 3. Okay. So, I hope you guys understand the basic concepts of the random variables. So, we are trying to get into the basics of random variables. So, these 3 concepts are important for us to get to the basics of random variables. Now, the next concept is, now when we talk about experiment, sample points and everything, then what are random variables actually? How do we define a random variable? Okay. So, the first thing is, there are many definitions. Okay. Textbook, etc. But since it is a practitioner's course, let us see what the practitioners think about it. For practitioners, the following definition, the following should work. Okay. So, this definition is more meant towards the practitioners. It is a function, or think about it as a rule. Think about it as a rule, okay, a rule of thumb or something like that, a rule that assigns a real number, that is, real number means any number between minus infinity and plus infinity. So, the entire scale, okay, any real number to each point in the sample space, each point in the sample space. Okay. So, let us consider, for example, let us consider the rolling of 2 dice. We already mentioned this example. If we are rolling the 2 dice, then what are we going to say? If x is a random variable, x, capital X, is a random variable, or rule, okay, that corresponds to the sum of 2 dice, or sum of face values of 2 dice. If that is the case, we are looking at dice, then x assigns the value 7 to the outcome, 4, 3, okay, also 3, 4 as well. So, that means if you roll a die and if the random variable is the rule that says the sum of the 2 dice, the rule is sum of the face values of the 2 dice. If that is the rule, then if you roll 2 dice and you get the die 1 as face value 3 and die 2 as the face value, die 1 as the face value of 4 and die 2 as the face value 3, then this 7 is assigned to the face value of this. Similarly, 3 and 4 also, the dice will change, but the same value gets assigned to it. Okay. So, always remember, random variables are denoted by uppercase letters. Okay. So, typically you use capital letters, uppercase letters to denote the random variable. Okay. The value of the random variable, is denoted by lowercase letters. So, mathematically, if I say x equal to little x, then this is the random variable and this is supposed to be its value. Or another way to think about it is if I say x equal to 7 and then x, this capital letter denotes the rule sum of the face values, and then 7 is that the sum of the face values coming to be 7. So, this is the rule that assigns the real number to the point in the sample space, and the point in the sample space can be 4, 3 or 3, 4. Okay. There can be other points as well, but for the time being, as an example, this is what we are going to deal with. Hope you guys understand this part of the concept. So, we will get into the next one then. The random variables for us is typically divided into 2. Okay. There are many ways people look into it, and so let us think about it as this way. Random variables, as I said earlier, they are divided into 2. So, the first one is what we call as discrete RV is called random variables, okay, and continuous RV, random variable. So, we are going to talk about discrete random variables and continuous random variables. Okay. So, let us talk about the first one, discrete. Okay. So, we are now talking about discrete. A random variable x, is x uppercase x is said to be discrete if it can take an at most or take on at most a countable number of values. Let us say x1, x2, etc. Lowercase is used to denote the values. So, when you say countable, this phrase countable, what does it mean? Countable implies that the set of possible values can be put in a one-to-one correspondence. Okay. Please check my spellings because I am not very good with this. Corresponding one-to-one correspondence with set of positive integers. Okay. This is what the discrete random variables is talk about. Okay. So, if you can connect it, so if you think about the random variable x, so let us think about an example. We talk about the random variable x, where x is the sum of the face values, of two dice. If that is the case, then the sample space of S is equal to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Sorry, this is a set. When you say 2, this implies the face value of 1 and 1, and 12 the face value of 6 and 6. All other possibilities are mapped into different values in this. Okay. So, if you have to 3, it will be mapped to 1 and 2 and 2 and 1. So, both will be mapped by this random variable 3. Okay. So, these two outcomes are mapped by 3 in this case. All right. So, if that is the case, then we talked about a countable set. What is an example of a countable set or a count? Then what is an example of an uncountable set? So, example of uncountable, okay, thing that you can't count. An uncountable set is all the real numbers between 0 and 1. So, here you can have values like 0.12379, then there is another value called 0.3468, 2943 like this. So, you can have infinite numbers between just 0 and 1. Okay. So, if that is the case, consider a random variable that can take an uncountably infinite number of different values, okay, different values. For example, like all non-negative in real numbers. So, think about a random variable that can take uncountably infinite number of different values. Okay. So, for time being, let us consider it as a promising candidate promising candidate for continuous random variable. So, what we are doing here is that the countably infinite number of different values, they are promising candidate for continuous random variables. We have not defined continuous random variable yet, but for the time being let us consider it that way. Okay. If that is the case, then let us look into the probability. Okay. So, it is easy to describe probability in terms of the discrete random variables, and then we will move to the continuous random variables little later down the road. So, for that we need to look into the concept of event first. Okay. So, what is event? So, again it is a practitioner's definition. From practitioner viewpoint, practitioner or practitioner's view, what is it? It is defined, it is a set of, it is not defined, it is a set of outcomes of an experiment. So, which means it is a subset of the sample space. Okay, so subset of the sample space to which a probability assigned, to which a probability is assigned, Okay. So, what we are basically saying is that if you say if you are rolling a fair die, so if you say the experiment is rolling a die and then you get the sample space to be values 1, 2, 3, 4, 5 and 6. Okay. If I say that the random variable x is equal to 3, which means if x the random variable is getting a face value of 3, then the probability, this event is rolling a die, the event is rolling a fair die and getting face value of 3. Okay. The random variable is like the face value. Okay. The event is getting the face value equal to 3. If that is the case, then what is probability? Okay. Probability has many measures or many definitions, and the typical textbook definition is the measure of likelihood that an event will occur. Okay. You are measuring the likelihood that an event will occur. This is what the book definition says. From our viewpoint, let's for the practitioner, what is it? It is a measure. It is a measure of the extent to which an event is likely to occur, measured by the ratio of favorable cases to the number of possible cases. So, what we are saying here is that probability, let us denote it as P, is equal to the ratio. So, it is a fraction of the number of favorable cases. Okay. How many of these are the favorable cases for the thing that you are trying to measure, for the favorable cases of the event in consideration. If that is the case, then to the total number of total possible events. If this ratio, if you calculate, this ratio is what we call as the probability. Okay. So, if that is the case, so let us see how to do an example. So, I said earlier rolling 2 dice, rolling 2 fair dice and summing the face value, If that is the case, the sample space we had denoted earlier as 1 1, 1 2, etc., all the way to 1 6, then 2 1, 2 2, all the way up to 2 6, then similarly 6 1, 6 2, all the way up to 6 6. Okay. And we said there are 36 of them in total. We also saw how to calculate the 36. This is the rolling of the fair die. This is the outcomes of the experiment. The experiment of rolling 2 fair dice. Okay. The experiment is rolling 2 fair dice, and the sum, okay, sample space of the sum or sum of the faces can take the values of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That is what we said. These are the face values it can take. Okay. And we said this is a discrete random variable because this is countably finite, okay, countably discrete. Okay. This is a discrete random variable. So, if I say that if the event is rolling 2 fair dice and getting the sum as 7, if that is the case, then the random we seen already it is equal to x equal to 7. So, in probability it will be probability of x equal to 7. That means rolling 2 fair dice and getting the sum to be equal to 7. What would that be? To calculate that, this is number of times the sum of 7. This is your event. Okay. Event will occur by number of total occurrences. This we have already seen it as 36. We see the 36 as the total occurrences. So, that will become its equal to 36 over something. What are those over values? So, one way to get 7 will be, in the first case if you have 1 and 6 it will be 7. Second case it will be 2 and 5, that will also give you 7. Then there will be 3 and 4, okay. Then there will be 4 and 3, which is the first die will give you 3, second die will be 4, this 4 and 3. Then the third one, the other case will be 5 and 2, okay. And the last case will be 6 and 1, okay. If this is the case, then you see this is 1, 2, 3, 4, 5, 6. So, there are 6 possible ways you can get 7 and there are 36 possible ways. So, your probability is 6 over 36, which is over 1 over 6. So, this is how you call the probability, calculate the probability of this particular event. Okay. So, this is the probability that the discrete random variable x takes the value of 7. What does this x denote? X is the rule and the rule is sum of faces. Okay. So, this is called as a probability of the discrete random variable or discrete event. Okay. The event is that you are rolling a die and rolling 2 fair dice. Okay. Okay. So, then from here now we are going to move into the new concept called probability mass function. Okay. So, earlier as we said that we said that probability that the discrete random variable probability that the discrete random variable x takes on the value little x, okay, is given by probability of x I, which is equal to probability of x equal to x I, okay, for I equal to 1, 2, 3, etc. So, this is the notational way of writing that probability that the random variable x takes the value x, little x, and for each individual case, I for 1, 2, 3, 4, I is an index, it will take different values, and summation of all I p of x I is equal to 1. That means, all these probabilities, if you sum of them, sum of all probabilities is equal to 1, something like this. Okay. So, this means that all probability statements about x can be computed from p of x, okay, or at least in principle. So, in principle you can calculate all probability statement x about x. So, this is called as the probability mass function of x. Mass function of x. So, if you have, say that, let us think about the example of rolling 2 fair dice, then if we say probability of 2, which means probability of x equal to 2, when you are rolling 2 fair dice and looking at the sum of the values, then this is equal to, we are saying the only one way to get this is face 1 and a 1 over the 36 of it, which is 1 over 36, like this. So, if I say probability of 3, then we are talking about probability of x equal to 3, which means you roll 2 fair dice and get the values, 2 face values and sum them, and those values sum equal to 3, that is 1 2 and 2 1 over 36, which is 2 over 36, okay, number of favorable to total number of outcomes. So, if that is the case, hence we can write little x, the value of little x, we can write kind of a table where it starts with 2, then let us say you have 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. These are the possible values, and you have the p of x, the probability of x. So, this means probability that the x takes the value of 2, we already have calculated 1 over 36, 3 we have calculated 2 over 36, 4 is equivalent to 1 and 3, 3, 1, 2, 2. So, that will be 3 over 36. 5 will be, what are the values of 5? It will be 1, 4, 2, 3, 3, 2 and 4, 1. So, these are the values of 5. So, that will be 4 over 36. 6 will be 1, 5, 2, 4, 3, 3, then 3, 3, either way it is the same, you cannot distinguish between each other, 3, 3. Then there is 4 and 2 and then 5 and 1. Okay. There is no 6 0. So, if you look at it, 1, 2, 3, 4, 5. So, it will be 5 over 36. 7 we have already calculated as 6 over 36. Now, what will be the value of 8? How many ways you can make 8? So, you can't make it with the 1. So, it will be 2 and 6. Okay. then obviously then with 3 you can make it as 5, then you have 4 and 4, okay. Then you have 5 and 3 and 6 and 2. So, 1, 2, 3, 4, 5. So, it will be 5 over 36. Similarly, 9 will be 4 over 36, this will be 3 over 36, 2 over 36, and 12 will be 1 over 36. 12 will be just the case of 6 and 6. Okay. So, this thing that this is this table, okay, or some people call it as the lookup table. Okay. This lookup table is the PMF, probability mass function of x, random variable x, which is about rolling 2 fair dice and taking the face value. Okay. So, now with this it is time for us to come to the definition of continuous random variables. Okay. So, what is a continuous random variable? We have earlier mentioned that if a random variable can be given the countably infinite values between two limits a and b, and all the real numbers, countably infinite real number values between the limits a and b, then that is a possible candidate for a continuous random variable. So, now let us formally define, because now we know what is a probability mass function and other things. So, using which we can now define a continuous random variable. So, what is a continuous random variable? A random variable, this is again the practitioner's definition. X is said to be continuous, if there exists a non-negative function, a non-negative function f of x such that for any set of real numbers or real number, any set of real number b, okay, probability of x element of b, the random variable is an element of b, is given by integral of b f of x dx. Okay. So, if you integrate this function within that particular b, any real number set, that will give you the probability, and integral of minus infinity to plus infinity f of x dx is equal to 1. If you integrate it across the entire set of real numbers, this is equivalent to say all probabilities sum to 1. Okay. So, this also implies that all probability statements about x can be, okay, or at least in principle x can be computed from f of x. Okay, the f of x is the function that we talk about, which is called, or which is called as the probability density function, probability density function for the continuous random variable x, Okay. So, in this particular case, continuous random variable is not necessarily just assigning of real values. It is the assigning of real values in such a way that there exists a positive function, okay, or a non-negative function f of x that will allow you to find the probability of x for any given set b and if you integrate this function from minus infinity to plus infinity, the value will be equal to 1. If that is the case, then this is called as the probability density function PDF of x. Okay. So, PDF is typically used for continuous, and for PMF is used for discrete. Okay. All right. So, using this you can find the probabilities at any given point, any particular probability statement can be calculated. So, let us give an example, let us take an example, okay, example to denote this. All right. Assume that between two values in R is a set of real numbers, A and B, okay, these are the two values, such that A is less than B. Okay. So, the two values A and B, and then such that A is less than B, and a random variable can take any value between A and B. The random variable can take any value between A and B with equal probability, any value can be taken with equal probability, which implies, or that is, all values between A and B are equally likely. If this is the random variable that any value can be taken between A and B with the equal probability, all values are possible with the equal probability, then you can think about it this way. If you have a graph, you want to draw a graph, this is the numbers going in X, your set of real numbers, and in which somewhere you have A and somewhere you have B, where A is less than B. If that is the case, and if you think about this is the f of x, the probability of this. So, between this A and B, all of these will have the same value. Okay. So, up to here it is 0, there is no probability. At A it will have one probability, and the same probability will remain until you reach B, and after B there is no probability, 0 probability. So, between A and B, any random variable you take, their probability is one and the same. This denotes the equally likely aspect, or same, okay, with equal probability, equally likely. Okay. All right. If that is the case, then any value can be given by f of x equal to, can write a function, we say 1 minus 1 over b minus a. So, if you take this difference, this is b minus a, take the difference and find the ratio of this, then this will give an equally likely probability for all values between a and b. Take any value between a and b, this is the equally likely probability, or 0 otherwise. Okay. So, for all other places this probability is not defined. So, if that is the case, if you want to find, so to find probability of x equal to little x, that is the case, then it amounts to integral minus infinity to x f of x dx, which is equal to integral minus infinity to a f of x dx plus a to x f of x dx. This is integration by parts, and we know that within these limits it is 0 because the function is not defined. So, this goes to 0. You only need to do is this integral, which is equivalent to integral a to x 1 over b minus a, that is your f of x dx, which is equal to x within the x over b minus a, which is equal to a and x. Okay. So, if you do this, this is x minus a by b minus a. So, this equation, this closed form equation that we write here, this tells you what is the probability of any value of x between a and b. This can be called as the PDF, probability mass function is for discrete, as the PDF of x. Okay. All right. So, with this we kind of look at the our discussion on probability, quick discussion on probability for the practitioners come to an end. And I know there is so much more associated with this about hypotheses and all those kind of things, which we will discuss in the later classes to go. But the most important part of this is everybody should realize that the concept of probability can be addressed in this particular fashion, and this is the basic building blocks of the probability, and from here we can actually build the larger theorems. And these probabilities are important, especially when you are doing analytics, because when you are having a hypothesis and when you are trying to do hypothesis testing, you will be dealing with different probability distributions and other aspects as such. So, thank you for your patient hearing, and we will see you in the next class. Thank you.